In this video, I'm planning on showing you how you would apply the first law to open systems that are steady flow. So in a previous video, I derived the first law for steady flow in open systems. And so I'm just going to write down the two equations that we derived for steady flow, and then we're going to look at how those equations are going to be applied to specific devices such as nozzles, diffusers, pumps, etc. So first of all, if we have we have Q minus W is equal to, and then this is if we have more than one stream out or more than one stream in, we're going to need to sum those streams. So this one's out. So then we have m dot out, and then this is the enthalpy out plus the kinetic energy out plus the potential energy out. And then we have minus, and then we're going to sum these streams as well. So we have m in, and this is m dot, multiplied by the enthalpy in plus the kinetic energy in, and this is in, plus the potential energy in. So this is our equation for the energy balance. This is the first law for a steady flow problem that's open system with multiple inlets and outlets. If we only have one inlet and one outlet, we can then assume that it's single stream steady flow. So first law, open system for what's called SSSF, and this is single stream steady flow. So this equation, so if it's single stream, that means that the mass in, and if it's steady state or steady flow, that means that the mass in is equal to the mass out. So we can just say that this is the mass flow rate. And then we can combine our terms from this top equation. So if m out and m in are the same, we can combine them. So that's what we're going to do in the second equation. So we have Q minus W is equal to the mass flow rate multiplied by the enthalpy out minus the enthalpy in plus the kinetic energy out minus the kinetic energy in plus the potential energy out minus the potential energy in. So this is our equation. This is our equation if we have a, so this is the first law for a single stream steady flow open system. So now what we want to do is see how these equations apply to certain systems. So let's just start with, so let's just say devices, you would use this equation for. And so we're going to look at nozzles, diffusers. And nozzles and diffusers are basically the same thing, they just do the opposite. There's opposites. So pumps, compressors, turbines, throttling devices, heat exchangers, mixing chambers, and last we're going to look at pipes. So let's start with nozzles and diffusers. So what we're going to do is apply this first law energy balance to nozzles and diffusers. So nozzles and diffusers are single stream steady flow devices. So we can specify that. And let's just draw a picture of what they would look like. So this would be a nozzle. So a nozzle is going to have low velocity in and high velocity out. So this is low velocity and high velocity. So basically what's happening is we're increasing the velocity at the expense of pressure. So this increase in velocity is causing a drop in pressure, and we know that from Bernoulli's principle. And so we're basically giving up pressure to increase our velocity. And then, so this would be a nozzle. And then a diffuser is the opposite. So a diffuser has high velocity at the inlet and low velocity at the outlet. So this is high velocity and low velocity. And the reason why we would want a diffuser is sometimes we'll have fluid moving through a system where we want to drop the velocity. So let's look at a few things. First of all, let's write our first law for single stream steady flow, and then just figure out which terms we're going to need for the nozzle and the diffuser. So we have the Q minus W is equal to m dot, because this is just single stream. And then we have our, and I'm going to change the enthalpy out and enthalpy in to just H2 minus H1 plus V2. So this is our kinetic energy. Oops, that's V1 squared over 2. And then plus G, and then this is Z2 minus Z1. So first of all, these are passive devices, so that means that the work is normally 0. So I'm just going to specify that it's because these are passive devices. There's no work input or output. And the other thing is, if there's no heat transfer, or if the nozzle or diffuser is well insulated, we can often say that there's no heat transfer. So if well insulated, Q dot is 0. So if it's well insulated, we can say that there's no heat transfer in or out. And assuming that these don't have a large height change, and you would need probably several meters before potential energy would even matter. These usually don't have large height changes. We can say that the potential energy term is 0. So usually no large height changes. So basically our velocities are changing, so we need to consider the potential energy and we need to consider the enthalpy. So basically we end up with Q is equal to m dot, and then this is H2 minus H1 plus the velocity squared minus the velocity squared, so that's out minus in, over 2. So this is our equation that we can often use for the first law, energy balance, if we have a nozzle or a diffuser. And remember, we can often assume that Q is 0 if it's well insulated. So if you have a nozzle or a diffuser, often you can just go use this equation, but you want to make sure you understand the assumptions that are worked into this equation. So we're assuming that, first of all, we're assuming that it's single stream steady flow. We're assuming, and basically a steady flow means that it's not in a startup or shutdown phase, so it's been flowing for a while, and the mass into the nozzle or diffuser is equal to the mass out. We're also assuming that the change in potential energy is negligible, so in other words, there's not a large height change. And we're assuming that there's no work input or output. Alright, so that's for a nozzle or diffuser. Now let's look at pumps, compressors, and turbines. So pumps, compressors, and turbines. So first of all, pump and compressor are basically the same thing. A pump is just used for liquids. So like if you have a liquid, you'll refer to this as a pump, and remember, a pump increases the pressure of your fluid. So it does work on your fluid and it adds pressure. A compressor is for a gas or a vapor. So a gas or a vapor, we're going to refer to this as a compressor. And a turbine does the opposite of a pump. So a turbine drops the pressure and it gets work, extracts work from the fluid. So a turbine is a pump or compressor that works in reverse. Basically, these pumps, compressors, and turbines most of them are centrifugal devices. So in other words, they have a rotating blade that's hooked up to either a motor or a generator. So pretty much all of these have some sort of rotating blade, and this blade is hooked up to a motor or generator. So hooked up to motor or generator. So a pump or a compressor is going to run a motor, or if we have a turbine, if a turbine's hooked up to a generator, so say in a power plant, that turbine is going to generate electricity. So basically for all of these, we're going to have work. And let's just go back and rewrite our equation so this is our first law, energy balance. So Q, and this is single stream steady flow. So we can start with the first law for single stream steady flow. So Q minus W is equal to m dot, and then we have H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. And so let's look at some of these terms. First of all, our work is not going to be 0. We're either going to have work in or work out. If it's well insulated, we can assume that Q is 0. So I'm just going to specify if well insulated, Q is equal to 0. That's only if it's well insulated. Turbines often are, so you can often assume that that term is 0 for a turbine. And then we also don't usually have a large change in the potential energy, because usually there's not a large, like if we look across, like, so let's say this is our pump. So if we look from here to here, there's not going to be a large height difference. So we can say that the potential energy is 0. And with a turbine, you might be thinking, oh, well, wait a second. Oftentimes when we've analyzed turbines, like we've had like water up here, and then we have our turbine, and then we have some water down here, and we've been saying, oh, well, the work is equal to the change in potential energy. So we have been looking at the potential energy, but you have to look at how you define your system. Like if we're defining our system like this, then yeah, we need to consider the potential energy, consider the turbine as our system. So this is our system. So we're looking from here to maybe here. So basically there's not a large height difference across the turbine. So then we say that the potential energy is approximately 0, but then we need to consider the enthalpy term for the flow work. And we also need to consider the change in kinetic energy. So we will have a velocity change. So that means that our equation becomes Q minus W is equal to m dot, and then this is H2 minus H1 plus V2 squared minus V1 squared over 2. And so this is our equation if we have a pump, compressor, or turbine. And so we're going to have work, and just looking at this Q, remember if it's well insulated, we can often assume that that term is 0 as well. All right, now let's look at a throttle. So basically what a throttle is a constriction followed by an expansion. So what this is going to do is reduce the pressure of your fluid. So we have a constriction followed by an expansion. And this is going to reduce the pressure of our fluid. So the reason why we would want to do this is if we need to drop, like let's say we have a water filter and we don't want high pressure fluid flowing through our filter, but the piping system might have high pressure fluid flowing through the pipes. So what we might want to do is drop the pressure in the fluid before it gets to the filter. And then after the fluid goes through the filter, then we'll increase the pressure again with a pump or a compressor. With these throttling devices, let's write down our equations. So these are single stream steady flow devices. So there's one stream in, one stream out. So we have Q minus W is equal to m dot, and then this is H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. So let's figure out what our terms are. Often these are well insulated, so we can often say that Q is 0. They're passive devices, so there's no work. So passive, no work. The velocity is basically the same, like the velocity going in is basically the same as the velocity going out, so this term is 0. And there's often not a large elevation change, so this term is often 0 as well. So basically we're left with 0 is equal to m dot H2 minus H1. So basically we get that H2 is equal to H1 for a throttling device. And so this is the equation for the first law energy balance that you can often use if you have a throttling device, but you need to remember all of the assumptions that are worked into this equation. So for instance, if it's not well insulated, so say you have a heat flow in or out, you're going to need to consider the Q dot term. So just make sure that you understand the assumptions that are going into this equation before you use it. All right, now let's look at some steady flow devices that aren't single stream. So they might have one stream, they might have multiple streams in and multiple streams out. First of all, let's look at a mixing chamber. So a mixing chamber basically takes whatever your fluid is. So here's our fluid coming in, and mixes it. This is kind of a bad drawing. So let's say that these are our two streams in. The fluid is being mixed and then it flows out. So basically we have two streams in, and this might be like hot and cold water or something else that we're mixing, and then we have a stream out. So these are both in and this one is out. So first of all, let's write down our equation for the first law energy balance, and this time we're going to need the one with the summations because we're going to need the summation for in, but out we just have one stream. So we have Q minus W is equal to m dot out, and there's only one stream out, so we can just write it like this. So we have H2 plus V, and I'm going to change this to out. So this is V out squared over 2 plus, and let's rewrite this. So this is H out, and then this is G Z out, and then we have minus and then we need to sum our streams out. So we have, or in, so we have in, so this is m dot in, and then this is multiplied by h in plus v in squared over 2 plus g z in. So now let's figure out which terms are 0. First of all, these mixing chambers are often well insulated, so we can often assume that Q is 0. So this is 0 if it's well insulated. If it's not well insulated, that term isn't going to be 0. So make sure that you know that before you assume it's 0. And then these are passive devices, so there's no work. So passive, no work. And also the velocities in these mixing chambers are often really low and unchanging. So basically we can assume that the change in velocity is approximately 0. And there's also usually not a large change in elevation, so we can often assume that the potential energy is 0 as well, so, or the change in potential energy. So basically we get that 0 is equal to m dot out, h out, minus the summation in of our streams in. So mass in, h, the enthalpy in. So basically we end up with m dot out, h out, is equal to the summation in of m dot in, h in. So this is our energy balance. So first law, energy balance for a mixing chamber, and this is with one exit stream. So remember with this, just remember the assumptions that go into this. We're assuming that it's well insulated. We're assuming that there's not large changes in the velocities. We're assuming the elevation is approximately constant. And we're assuming that there's one exit stream. All right, so that's the mixing chamber. Now let's do a heat exchanger. So for the heat exchanger, and we're just going to look at there are a lot of different types of heat exchangers. We're just going to look at a really generic heat exchanger for this example. So let's say that we have two concentric pipes, and let's say that we have fluid flowing through the inner pipe in one direction, and then we have fluid flowing through the outer pipe in the opposite direction, and we're trying to cool the inner pipe. So let's say that we have heat transfer from well, not really heat transfer, but there's going to be heat exchange from the inner pipe to the outer pipe. We can also have heat exchangers like this, like let's say that we have this heat exchanger, and let's say that we have fluid flowing in here, out here, and then let's say that we have a pipe through here, that we also have fluid flowing through this pipe. And let's just say that the fluid flowing through this inner pipe is being cooled. Heat exchangers have multiple inlets and outlets, so we need to start with our first law energy balance that accounts for multiple inlets and outlets. So we have Q dot minus W dot is equal to the summation of the mass out, and then this is enthalpy out plus the kinetic energy out plus the potential energy out, and then this is minus, and then we have the summation, and this is in, so m dot in multiplied by h in plus v in squared over 2 plus g z in. And so now we want to go through and figure out which terms we need to account for and which ones are 0. So first of all, if we look at these two heat exchangers that we have up here, I'm going to consider this Q in, Q out. So I'm considering our heat in and heat out. First of all, we want to define our system. So we're going to say that our system is this. So basically our system includes both pipes, and the same thing with this one. Our system would be this. So basically our system includes both pipes. So if these are well insulated, which they often are, then there's no heat out or in. So that means that Q dot is equal to 0, assuming that these heat exchangers are well insulated. So we can often say that Q dot is 0 if well insulated. So pay attention to that though, because if your heat exchanger isn't well insulated, then you can't assume that that's 0. These are also passive, so there's no work. So passive, no work. And often the elevation change isn't very large, so we can often assume that the change in potential energy is approximately 0, so delta PE is approximately 0. Although, if you have a large change in elevation with your heat exchanger, you might not be able to assume that, so just make sure that that's true. And then often the velocities through these heat exchangers are pretty slow and they're not really changing. So that means that the change in kinetic energy is also approximately 0. So that means that these two terms are often 0 as well. So let's rewrite this equation. This becomes the sum of our outlets, so m dot out multiplied by h out, is equal to the sum of our inlets, so m dot in multiplied by hn. So this is going to be our first law energy balance for a heat exchanger, assuming that it's well insulated and that we don't need to take into account the velocities and we don't need to take into account any elevation changes. So if you do have some large changes in velocities in your heat exchanger, you would need to also account for the change in kinetic energy, or if you have heat in or heat out, like let's say it's not well insulated, you would also have to account for that. But in general, this is the energy balance that you'll be able to use for a lot of heat exchangers. So now let's talk about pipe flow. So pipe flow might have actually been better to fit under the single stream steady flow devices, because the pipe flow is going to be single stream steady flow. So in a pipe there's flow in and flow out. So let's say we have our pipe, we have our flow in, and we have our flow out. And flow through pipes is usually steady flow. So unless you're with any of these, if you're in a startup or a shutdown phase, so let's say you're analyzing the first couple seconds when your device first starts up, or the couple seconds after it shuts down, you're not going to be able to assume steady flow. But in general, if you assume that the flow has been going on for a while, you can assume that it's steady flow. Let's go ahead and write our energy balance. So Q minus W, and this is single stream again, so we can just use m dot. So this is H2 minus H1 plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. And so first of all, the Q, like this heat, often, like if you have a really long pipe and it's not insulated, the heat losses can actually be significant along a pipe. So this is going to be significant unless pipe is well insulated. Also, the work is going to be 0 unless you have a fan or maybe some electrical work in your pipe. So like let's say that this is our control volume inside the pipe. If we have say a coil in here, so we have so we're heating the fluid in the pipe, we would have electrical work that we need to account for, so then the work term won't be 0. Or if we have a fan, like let's say we have a fan that's moving the fluid in the pipe, we would have work from that fan. Although often with the fan it's small enough that you can neglect it, but if you do have a fan, it's something that you might want to consider. The velocities are often low in pipes, so often, and they often don't change much, so often the change in kinetic energy is approximately 0. However, the change in potential energy, if your pipe has a large elevation difference, which a lot of pipes do, like you'll see pipes that are running and then they have a large drop. So let's say this is our pipe. We would need to consider that potential energy in our pipe. If your pipe is all one level or one elevation, then you can assume that the potential energy term is 0. So let's rewrite this equation. So we have Q minus W is equal to m dot H2 minus H1 plus, and then we're assuming that the kinetic energy is approximately 0, although that might not be true. If you have a pipe that has a large change in kinetic energy or a large change in velocities, then you'll need to consider the kinetic energy term. So this is GZ2 minus Z1. So I almost hate writing an equation for the pipe because there's so many variations in pipes compared to some of the other devices we looked at. So with pipes, it might almost be better to start with this equation and then just cancel out the terms that are 0. But if you don't have a large change in velocity, you can assume this equation here, and then you can also assume that Q is 0 if your pipe is well insulated. So we've gone through a few different devices, and I'm just going to go back and summarize these. So first of all, if you have a nozzle or a diffuser, you can often, so it's passive device, so your work is 0. And if it's well insulated, you can assume that Q is 0 as well. And if there's no large height change, you can assume that your change in potential energy is 0. So we end up with this equation for our first law energy balance for a nozzle or a diffuser. For the pumps, compressors, and turbines, if we assume that it's well insulated, we can assume that Q is 0. We can also assume that the potential energy is approximately 0, assuming that we don't have a large height difference. But there will be work input or output. So this is our first law energy balance if we have a pump, compressor, or turbine. If we have a throttling device, first of all, if we assume that it's well insulated, we can say that Q is 0. If we say it's passive, well, it's passive, so there's no work. The velocity in and the velocity out are approximately the same, so your change in kinetic energy is 0. And if there's no large height, no large elevation change, then your change in potential energy is approximately 0. So that means that we end up with the enthalpy out is equal to the enthalpy in for a throttling device. And then with a mixing chamber, so all of these up here were single stream steady flow devices. The mixing chamber is not a single stream device because we can have multiple streams in. Usually there's one stream out. If we assume it's well insulated, we can assume that Q is approximately 0. If it's passive, so there's no work, the velocities are often slow in these mixing chambers, so the change in kinetic energy is usually approximately 0. And then if we assume that there's no large elevation change, then the change in potential energy is also approximately 0. And we end up with this equation for our first law energy balance for a heat exchanger. And this one is assuming that we have one exit stream. And then we looked at a heat exchanger. Heat exchangers can have multiple inlets and outlets, and They often have, so if they're well insulated, we can assume that the heat in or heat out is zero. They're passive, so there's no work. The change in kinetic energy is often approximately zero because often the velocities are slow and they don't change much. And if we don't have a large elevation change, we can assume that the change in potential energy is approximately zero. So we end up with this equation for the first law energy balance for a heat exchanger. And then for pipe flow, there are a lot of variations we can have with pipes. So I think it's often best to start with just the general energy balance equation. But then we can go through and say which terms are zero depending on what our system is. So if the pipe's well insulated, often Q is zero. If there's no work input, then we can, from say an electrical heating unit or a fan, the work term is often zero. Also, the change in kinetic energy is often approximately zero because the velocities are usually slow in pipes and there's usually not a large change in velocities. Also, if your pipes can often have large elevation changes, but if your pipe doesn't, then your potential energy term would be zero. So this is your equation, your energy balance for a pipe flow. This is the only assumption this equation has is single stream steady flow and that the change in kinetic energy is approximately zero. So let's just look at, so I've given you a bunch of different equations for the different devices, and basically we just took the first law that I had derived in a previous video for single stream steady flow devices and steady flow devices. So with all of these, there may be exceptions. So you need to read the problem carefully. So for instance, we said that heat exchangers are often well insulated. Well, what if it's not? Then you're going to need to consider your heat in or out. Same thing with a nozzle or diffuser. If it's not well insulated, then you need to consider the heat in or out. So you need to always read the problem carefully and make sure that the equation you're applying applies in your case. So in the next video, I'm going to start working on some example problems of how to apply this energy balance to these different types of devices.